Well, welcome, folks. Friday afternoon, I thought we'd have a little bit of fun. How's the conference been? I mean, good? Are you getting tired? Like 3 days is a lot. Especially, did you do workshops first, too? A few folks? Yeah, okay. It's a lot in a week. Admittedly, this is a bit more of indulgent of a talk. Are there folks who've listened to Geek Outs before and know what I'm talking about? So if you haven't run across these, I'm one of the .NET Rocks guys, and I'm responsible for the Geek Out episodes. It was Carl's idea. I thought it was a dumb idea, and I was wrong. And now we've made a better part of 100 of them, but they're all the geeky subjects that I'm interested in, which turns out to be pretty much everything. But I'm good at putting information together and reading papers and then telling a story around it. And so in the old days, if you look at this list, we would do one a month. It was a lot of work, but it was a lot of fun. And these days, we probably really only do them at year end. Back in the old days, we were doing 3 episodes a week, and so I didn't feel so bad about taking one show a month out of 12 and saying, let's go talk about hypersonic vehicles. But now that we're doing one a week, I really only do these at the end of the year. And if you caught the last pair, these were over Christmas, New Year's, and I did one on sort of state of space, which I think I went 90 minutes on, and then state of energy. And this talk is very much that energy talk, although I've had a chance to tailor it more to the UK market. It's an excuse for me to read all of your government's paperwork about what they think they're doing with energy. And let me tell you, those guys write a lot. They are quite wordy. So we're talking about electricity here, and it's good to spend a little bit of time thinking about how we actually make electricity. The planet is largely dependent on it now. We consume about 15 terawatts at our peak consumption times, about 160,000 terawatt hours per year. So for better or worse, our civilization functions extensively on electricity these days. The key to the whole thing is the generator. This is the technology. The one that won out was Tesla's design. For the most part, it's been improved somewhat. There are a few different variations on it. But in the end, we have a shaft that's being spun by some other source to turn an armature inside a set of coils. And from that magnetic effect, we get a set of waveforms. Typical out of a commercial generator is a 3-phase waveform of electricity. And in some, I find it more common in the UK that homes actually have 3-phase power in it. It's not all of them. It's very unusual in North America to have 3-phase power into the house. They're usually only for commercial sites. We have what we call 2-leg power, which is even stranger. They're 180 degrees out of phase. And many places have a single leg, where they only take one. And we can talk about 240 volts versus 120 volts, 50 hertz versus 60 hertz. It's really not that important. I know you're really proud of your plug. The rest of us aren't, okay? But that's okay. The plug is fine. It's also, you know, the English plug is like Lego. It's the only thing you really fear stepping on. It's bad news. Primary way that we spin those generators is the steam turbine. So there are a variety of ways to make steam. It has to be high pressure steam, very high temperature. We typically think of steam from the kettle, about 100 degrees Celsius. The typical steam that comes into a turbine like this is about 300 degrees. So we have to do some tricks to get it that hot. And this is a 3-stage, almost 4-stage style turbine. And if I can play with my fancy Logitech here. So here's actually the high pressure stage. So that's the hottest steam comes in there first. And that spins that part of the shaft. And then the pressure is reduced because it's gone through the turbine blade. So it goes to what's called the 2nd stage area. And then this is the 3rd stage, or the lowest pressure. This is a very refined piece of technology. We have built these for a long time. We've built a lot of them. And it's why we tend to make power using water steam, because we're good at extracting as much energy from it as possible. And when we get into the conversation about making energy in general, in some ways this does hold us back. A lot of the technologies I'm going to talk about, they come down to this because it's known, reliable. The main thing that everybody looks for in electricity is that it works, right? We're very unhappy when it doesn't. And so there's a strong disincentive to innovate. And so now, as we're getting into the world as it stands today, we have a little more energy around that we need to innovate. Now, I'm going to talk about a lot of different energy types, and so it's good to have some common measure between them. And the usual one in the industry is called the levelized cost of energy. And the levelized cost of energy basically says how much does it cost to build the plant, how much does it cost to operate and maintain the plant and ultimately dismantle it over the amount of time versus the amount of electricity that it will generate, and that will give us a number, and it's typically dollars per megawatt. And I'm going to focus on the UK since we happen to be here, and the government provided me with this lovely diagram, which I really enjoy because I'm that kind of person. Because this is what we call the grid, right? It's at a very high level. We're not getting down to the nitty-gritty of the grid, but we're looking at the highest voltage lines that connect throughout the country. Notice tightly tied to Ireland, but also plenty of undersea wiring, connections to Norway, to Belgium, to the Netherlands, to France. No grid stands alone, except Texas. That's why theirs doesn't work that well, right? You make more than enough energy in the UK to supply all of your homes, but you also export a fair bit of it and import a fair bit of it, which I know seems odd, but the reality is that energy is an arbitrage business. And sometimes it costs more to make electricity and cheaper to buy. And sometimes it's smarter to sell and then buy some back. And so as much as you may no longer be a part of the EU, you still transit a lot of electricity backwards and forwards with a bunch of different nations. That's what a civilization looks like if you're going to have it work well, and you still do it. And those weird lines that just sort of stop in the middle of the channel, wind power plants. So you have to run a wire out to them to bring the electricity back on land. All right, let's go through some of the sources and how the UK use it. And we're going to start with coal for a very good reason. You guys started this. Now, to be clear, coal was discovered a long time ago. There is evidence of coal being burned back in prehistory. It was the rock that burns. But it was that guy, James Watt, and burning coal to make steam, initially to pump out mines, to manage water. Back in the 1700s, it really kicked off the industrial evolution as we know it. We're at the center of all that. The first coal-based electrical generation power plant was the Holborn Viaduct Station, which is about a half-hour walk from here. It was built by the American Thomas Edison, and it was a DC power plant for lighting streetlights, because at that time, you lit your streetlights with flue gas and caused fires accordingly. It ran for about 6 years until apparently too much bureaucratic red tape in the middle 1800s made him decide to shut it down. Now, that bureaucratic red tape was actually the UK government at the time trying to establish standards around electricity because different electrical supplies ran at different voltages and different cycle rates for different services. So to this day, you still have power plants that are named for the fact that they ran streetcars and ultimately the tube, and they typically ran at 23 hertz at 440 volts. Not the kind of stuff you want to boil a kettle with. And so the government tried to standardize it so you didn't have different sets of wires for every kind of power stacked on one on top of each other, that we could build common infrastructure across all of these things. And so at the peak of utilization in the 90s, or in the 70s, 90% of the power in the UK was made with coal. You mined a lot of your own coal, you still do. Most coal these days in the UK is mined for steel production. Anthracitic coal is a necessary part of making steel. Less of it's burned. You're down to less than 2% of your power generation done with coal. There's a handful of coal power plants left, and they are being shut down in the next couple of years. The last of them should close in 2024. And part of the reason for that is that coal power production is actually relatively expensive compared to other choices today. Typical LCOE is between $65 and $100 per megawatt, which is now considered pricey. The reality, of course, of operating coal is that you need a tremendous amount of the stuff. So you typically lay a lot of train lines in directly from the mine. The closer to the mine, the better. And you're perpetually, 24 hours a day, hauling in tons of coal, powdering it, burning it at high temperatures, doing your best to capture the output, to boil water, to spin steam turbines. And as much as we've tried to mitigate as much of the emissions from coal, we can't get rid of them all. So it's still a fairly toxic way to produce electricity. The effluent of coal burning is not good for you and not good for the planet. Once upon a time, we also burned oil. Then we decided that was dumb, better to put it into cars and distribute the burning all over the country. The few oil power plants that even existed in the UK converted to natural gas long ago, although most of them have actually been decommissioned and replaced with far more efficient gas power plants. Today, the combined cycle natural gas turbines power plant is the most efficient power plant that does base load burning of a hydrocarbon. So natural gas is relatively cheap. It is quite plentiful, despite what the Russians may have told you. It's common enough in extraction of various different sources that often it is simply burned off at the mining point. But you can capture it into pipes. You can liquefy it if you must, but generally using it in gas is the best way to go. The reason the combined cycle plant is so efficient, the big box on one side here, this thing, that's actually the air box to make sure that the air that it's bringing in to do all the burning, to provide oxygen for combustion is clean and efficient. Here we have the turbine part. So this is very much like a jet turbine. It's running on natural gas and it spins the generator. But it also produces a tremendous amount of heat. And so right beside this is a steam turbine. They use the excess heat to also generate steam and spin a spin turbine, which is why this gets to be so efficient. It utilizes that energy multiple times to extract as much electricity from it as possible. So not only does it create a fairly good amount of electricity for its size, it also produces the least amount of carbon emissions of a hydrocarbon-based power plant for the megawatts that it produces. And it's cheap, relatively speaking. These run about $45 to $75 per megawatt LCOE. And they're fast. So often these plants are put in place as peaker plants. Part of the challenge of running a grid is you have to make as much electricity as needs to be consumed at the time. Storing it is extremely difficult and is a relatively new invention. So normally all those folks that operate those power plants are literally spinning them up and turning them down based on your utilization. And of course, the UK is famous for there are certain television shows that when they end, everybody puts the kettle on. And there's literally people waiting to turn on power plants to deal with the end of Coronation Street. This is more than a third of power generation in the UK today is now natural gas. Some converted plants and some newly built plants. Natural gas is inexpensive. It does still have significant carbon emissions, so there are goals to move away from this. But if you're going to produce carbon dioxide from power, this is the least offensive way, and hopefully you'll get away from it entirely. The United Kingdom has some of the very first nuclear power plants in the world. You also had one of the very first nuclear accidents in the world. Congratulations. So going back to the 1950s, I did a whole geek out just on nuclear accidents, and I never mentioned the Windscale fire from '57, and I got a lot of nastygrams about that because most people think about Chernobyl, Fukushima, and 3 Mile Island, and arguably Windscale was worse than all of them except Chernobyl. Only Chernobyl blew a core across the countryside. But Windscale burned for 3 days, and that's really, really bad. It was also way at the beginning of nuclear power, and largely people didn't understand how serious the situation was. And those that did really didn't want to talk about it. So the situation made it far worse by the way that it was treated. That being said, nuclear power has matured dramatically. The power mix, at its peak, the UK made about 26% of its power with nuclear. Today, it is 16%, and it will go down before it will go up. There are only 5 major power plants still running. 4 of them are slated for shutdown in the next couple of years. Some have gotten extensions, like Sizewell. You use a relatively exotic form of power. The most common nuclear reactors in the world are the pressurized water reactors. So they take rods of uranium dioxide in casings in large assemblies. They stack them together in a big container of water. They then pressurize that water so that it can get up to the kind of temperatures needed to spin turbines. That water is in heat exchange with another loop of water, and then that actually spins the turbine. That's the most common kind. You have a couple of them, pressurized water reactors, but the common reactor is this advanced gas reactor. Many English reactors are like that, or this particular design, which uses carbon dioxide. It's an interesting system. It works very well. They're also getting old, and so you're turning many of them off. There are 2 new reactors being built in the UK right now. One is the Hinkley Point C, which actually started in construction in 2018. It's recently reported to be 50% over budget, and several years behind time now, expect to go into production by 2027. And then Sizewell C was only officially approved for development late last year. And so supposed to be ready to go by 2026. Nuclear power in this traditional format is expensive. The LCOE on it runs $130 to $200 per megawatt. So it's not cost effective compared to many of the other strategies to make electricity. And that's largely because every nuclear power plant site is a place for handling nuclear materials. And that is problematic. It means that its site has to be certified a great deal. It has to have a large exclusion zone. Several kilometers around it can generally not have anybody living in it. Because they refuel the reactors on the site. So they take those fuel assemblies out of the reactor and they put new ones in, or they'll actually modify them, shuffle them around to consume the fuel more efficiently. And all that fuel handling takes certification, it takes extremely qualified people, and it takes a very specialized site that needs to be routinely inspected. And I bring that up because as we talk about more modern approaches to nuclear power, we've addressed a lot of that. And now also being said, modern reactor designs are far safer than the older reactor designs. We don't have the problems that cause situations like Chernobyl, Fukushima, so forth. Fukushima is only 2011, but the reactor design was much older. There were 3 of 4 reactors that got damaged in Fukushima. There were actually 2 others that nobody ever talks about, reactor 5 and 6. They were running at the time of the earthquake, but they were a slightly more modern version of that same reactor that has passive shutdown. So even though they also got hit by the tsunami and their generators were also destroyed, didn't matter, they cooled themselves down. The older designs needed powered cool down, and they failed. Today, no reactor is built requiring active cooling. They all have passive shutdown solutions, and so are all the new reactors that you're building. I should talk briefly about biomass. It is a carbon-emitting power approach. Nobody builds power mass because they want to make electricity. What they have is excess materials available that can be made into power. These are power plants of opportunity, essentially. You'll find them around places that are manufacturing things that have agro-waste products. Like if you're refining sugar, you have an effluent that can be burned for electricity. They tend to be small, megawatt or 2 at most. The price, LCOE can be pretty good, down to $50, up as high as $150. But again, you wouldn't do these at scale, so you have several hundred of them scattered across the countryside. Wherever there are materials that would otherwise be a waste product can be made into electricity. And so I mention it just because, while it doesn't amount to much in the overall power generation, it makes less power than your coal power plants do. It is a source of power based on us trying to be efficient. Geothermal power is not something that you do in the UK. There's been a couple of experiments over the year, but for the most part, it doesn't happen. And it's funny because it's just not that far away. You've got Iceland, and that's all they seem to be doing these days. The reality, of course, is as you dig down into the ground, you hit hot rocks. And if you dig far enough, you hit really hot rocks. And if you send water down there, it will come back hot. And then you can spin turbines. The problem is that the drilling part is the expensive part. And your ground is notoriously hard and very, very difficult to drill into. And so it's just not a lot of incentive to develop that here. There are places where it's really the only choice, Iceland being one of them, where it's hard to make power almost any other way. And their depth of drill is very short. If you can drill less than 2 kilometers, geothermal becomes a much more effective strategy. That being said, and I mentioned this in the last Energy Geek Out, there is a new technology available for geothermal using high-energy microwaves to do the drilling. And this is an important innovation because normally when you're drilling with a grinding tool, the grinding tool is being destroyed in the process. And the harder the rock is, the more often you're going to need to replace those tools. And as you get down deep, you have a lot of pressure involved. And so you're pumping drilling mud to try and maintain your drill, as well as remove the materials and pump back up again. And so shutting down to replace a drill bit is a very complicated and costly process. You're also inserting casings to keep the drill hole from collapsing. All of that is complex. And in something straight out of Star Trek. They've made this large, extremely high-powered microwave that vaporizes rock, and in the process deposits it on the side of the hole that it's making to be a natural casing as you go. I mean, it sounds like a science fiction novel until you see the video of them doing it. You're like, okay, that thing's badass. It's very short range, so it's not good for a weapon. Like, you can't go up and hold it against a guy and say, hold this for a second while I turn this thing on. But in the prospects of drilling a pipe 4 to 5 kilometers underground, it's very interesting. And so that's a new technology just beginning to come down the pipeline that may open geothermal for a lot of us, because geothermal essentially has no emissions. If you do it properly, which is that you have a closed loop heat loop where you're pumping water down in sealed pipes and it's coming back up another pipe as steam, and then you heat exchange against it to actually spin your turbine and send that same water back down again, you'd almost have no emissions of any kind. And you don't really need other sources of water. Like, it becomes a really interesting solution. So we may see more of this in the future. Diesel electric power, if you have an urge to spend a lot of money on electricity, this is the way to go. So you're literally talking about making a giant diesel engine. Giant as in the fuel tank will be underground. The oil tank will be underground. You'll have a series of motors that are connected to those loops, and you run them 24 hours a day to spin generators to generate electricity. But again, depending on your location, this may be the only choice. So you look at places like the Galapagos Islands. It's technically not inhabitable by humans, but if you put in a power plant like this, typically no bigger than 5 to 10 megawatts, it's enough to sustain a small population of people with electricity. And in the case of Galapagos, they use a bunch of it to desalinate drinking water from the ocean, too. The UK doesn't use these. There's no reason to. It is very much the power of last resort. Hydroelectric. Not a huge amount of power in the UK made with hydroelectric. I'm from British Columbia, where we got mountains, so that's what we do. And the Norwegians, very much the same situation. They tend to be very large projects, so they're costly to develop, but they last an extremely long time. Typically, many power plants are good to 20 to 40 years, sometimes 50 or 60. Hydro runs 100 plus with maintenance. You can keep them going for a very long time. So the price comes in at an LCOE of around $40 to $50. That's pretty effective. You do have some hydroelectric. It's still only about 2% of your power. But the Calder Water power plant, 6 gigawatts. That's a good size dam. And as long as you have water, they keep working. Sometimes you don't have water, just ask the Hoover Dam. All right, let's talk about the new stuff. Let's talk about onshore wind. So the UK is an interesting mix of both onshore and offshore, sort of equal. Wind power is the growth area. It's also currently the cheapest source of electricity available on the planet today. So an LCOE of around $25 to $50. So $25 a megawatt is very, very inexpensive, and it certainly creates part of the appeal of that. And there's a reason for that. The amount of money that's been spent developing wind energy is extensive, and so today we have multi-megawatt offshore wind turbines. They are massive and incredibly reliable. That being said, 20 years is typically the lifespan for a wind turbine, and you'll change out blades and replace components over time. So you have about 11,000 turbines in the UK these days, split evenly between onshore and off. The onshores are smaller, cheaper to install. They're not as popular with the populace. People don't like looking at them. They do make some noise. There is the issue of bird strikes, although I would argue that the current metrics show that as many as 500,000 birds are killed per year by wind turbines, compared to 2.5 million birds killed by domesticated cats. So if you're really worried about the birds, keep your cat inside. I mean, not that every cat kills birds, but there was this great study at the University of Virginia where they put cameras on domestic house cats that are normally outside, and it's like only 20% of them killed, but they were psychotic murderers. They killed constantly and clearly for fun. So yeah, if you got one of those cats, you can make a big help by keeping that one inside. So onshore, well known, kind of at its limits for what it can do, and there's only so much land to go around. Offshore, clearly more interesting, although there's really two classes of offshore. The typical offshore, and certainly what exists in the UK, is more of a near shore system, typically no more than 50 meters of water, which is most of the channel. So if you remember that map that I showed briefly, all of those wires are sort of ending in the water. We're all in the channel because the water's shallow. And so literally you're driving a casement down into the bottom from the surface of the water, draining it, pouring a bunch of concrete into that shaft, and sticking the wind turbine on top. And then the rest of it can be maintained over time. And these still have shorebird issues, and they are only in certain locations. So it limits where you can put them. They can only get so big. They are hazards to shipping, so they try and keep them set in certain areas. There is development going off in true offshore wind. So this is wind with stabilized platforms. They're floating platforms that have cable anchored, or there's a few different ways to stay them. This is directly derived from the oil rig industry. So they're going to be more expensive to make, but they can be dramatically larger. And wind flows further offshore are more stable, and the bigger platforms allow them to get to better wind, all in all. So this probably is the future of wind power. You will still have the problem of they need to be maintained, so folks need to go out there to do work on them, and you do need to get the power back to shore, so you're running very long cables. But in exchange for, they are out of sight, so out of mind. They're in the bigger ocean where there's room to move around, and generally fewer problems with hazards of navigation. And we're certainly getting the build quality. This will probably continue to be the least expensive power going for quite some time, and it has a lot of advantages. Solar. I'm going to start with solar thermal because everybody talks about voltaics, but solar thermal is also a form of heat. This is what they call a heliostat type solar. This is actually one of the plants that's in Morocco. So what you're doing here is you have electrically guided mirrors. Every one of those dots is a mirror with a 2-axis motor on it that can constantly adjust itself to reflect the sun into that central point at the top of the mast. And at the top of the mast is a big block of graphite that's pumping a lithium beryllium salt through it. Now, lithium beryllium fluorine salts are only a liquid at 400 degrees centigrade, but they stay a liquid until 1500 degrees centigrade, as opposed to water, which is only 0 to 100. So there's some advantages to using those kinds of salts heated by the sun. They can hold so much heat, they'll run overnight. So even when the sun's down, you have enough heat left in the salt loop that you can continue to run turbines 24 hours a day, if you can get to sufficient size. Unlike photovoltaic solar panels, they don't care how hot it gets. Solar panels really don't like heat. Heliostats couldn't care less. So this is why places like Morocco built these gigantic gigawatt power plants running on salt, so they are 24-hour-a-day power, just powered by the sun, as long as there's sun every day, which typically there is, but it won't last more than a couple of days. Unfortunately, operationally, they are still expensive, $120 to $150 per megawatt. And the reason is a lot of maintenance. All of the motors for all of those heliostats need to be routinely maintained. The heliostats have to be kept clean. The salt loop is the least maintenance part of the system. It's quite immature, but to collect that much sunlight takes a bunch of moving parts, and moving parts in deserts have their challenges. Photovoltaic is the second cheapest power source out there at the commercial scale. So when you're building commercial large arrays of panels collecting sunlight, it becomes quite expensive. We largely have the Chinese to thank for this. They were the ones who built built solar panel factories at such a scale that they drove the price down to that, again, in the $28 to $35 per megawatt class. Very, very inexpensive power. Now, the technology is interesting. It is layers of silicon and a few other substrates. It's manufactured much the same way that our microprocessors are made, which is part of the reason we were able to make them relatively cheaply. They only collect about 20, maybe 22% of the sunlight they hit. If you're standing on the equator at noon, when the sun is directly overhead, you get about a kilowatt of sunlight hitting a square meter. It's about 1,400 before you go through the atmosphere. You lose a bunch of it to get through the atmosphere. That's when the atmosphere is effectively the thinnest. It's perfectly clear. This is the optimal situation. And then with a typical, this style of photovoltaic, you're only going to collect about 220 watts of that. Now, let's get off the equator and up here in the land of the gray. And so we have more atmosphere to go through. We don't have as much clear sunlight days. but because these panels are so cheap, it's worth it. The Germans spent a lot on this, and they have now learned to stop pointing their panels south. They point their panels east and west, because the individual panels are cheap enough now that we don't need power in the middle of the day. We need power earlier and later, and so we get less yield per panel for spreading out our power generation over the course of the day. But that's how far photovoltaic has come. So another downside, space consumption is substantial. So it takes about 20 times more land to generate a gigawatt of power with solar panels than it does with a traditional power plant like a combined cycle gas turbine. On the other hand, lifespans are good, more than 20 years, no moving parts, no fuel, relatively little maintenance. They do need to be washed occasionally. Don't let them get too dirty, and wiring does corrode. Like, there's some maintenance to be done, but the maintenance costs are quite low. The hotter they get, the less time they last. They prefer about 25 degrees centigrade, and so you would generally think in the UK that's not a big deal, but I saw what you did last summer, and that can cost you 0.5% per year in terms of efficiency. So they do decay over time. You don't tend to have very large solar plants in the UK. The biggest is about 75 megawatts, which is big. That's a lot of room, but there are gigantic ones in other places like Australia where they have lots and lots of land. But there's over 1,000 commercial solar power arrays in the UK now. So it's popular, and they're getting up to several percentage points of your overall power generation. Wind by far the most popular, but solar's doing well. We're starting to get clever with our solar too. We're doing things like putting them on the reservoirs of dams for a few reasons. I mean, one is that's open space. You know, it's typically not particularly biologically sensitive. You made the reservoir in the first place, so you can mess with it. The water helps keep the panels cool, so they last longer. And covering the water keeps the reservoir fuller. You reduce evaporation. In India, they're putting solar panels over top of their irrigation canals. It retains water, it generates electricity, and it decreases the amount of algal growth in the canals. So it's all mutually beneficial. In exchange for making a more complicated installation, often not in the perfect orientations, but has some advantages. Residential solar. Doing fairly. There's over 1 million homes apparently in the UK now that have solar panels on them, which sounds like a lot until you realize that's like less than 3%. So it's not wildly popular compared to a place like southeastern Australia where they're close to 20%. But they have a lot more sunlight. It's relatively expensive, $150 to $200 per megawatt LCOE, but that's not how you typically measure it. And as I get later into this talk, I'll talk more about what the power is of having solar local to your house. There are often buyback solutions, which seems to be common in the UK, where if you're making more power than you need, the power company will pay you something, typically as a credit, because you're going to need it back from them eventually anyway. Sometimes it's dark. But they say almost 6 gigawatts of power could be produced on an ideal day with the residential solar that exists inside of the UK right now. It will never be that much, because that's not how things work out, but it does speak to, there's a lot of solar panels out there. There are more efficient solar panels. These, arguably, the main feature of these silicon solar panels is that they're relatively inexpensive and they're reliable. They're a very known entity. We know how long they last. We know how they break down. We know how to maintain them. We know how to control them well. There's a popular technology being developed right now called perovskite solar. It's substantially more efficient. It's also very thin. They can even be made transparent. It gets up to about 30%. It also is a little less resource intensive. You don't need as much silica, you don't need as much titanium. However, they're a little pricey, and they have durability problems. They're very intolerant to excess heat, and so there's a lot of maturation that has to go into the development of these panels before they might be good enough for commercial grade. So if you're wondering, like, why are we still using the crappy solar panels? They told us there would be better ones. They're trying, but there's a lot of things that go into a workable power source. Both with wind and solar, we have the problem of sometimes it's not windy, sometimes it's not sunny, and we need power storage. Power storage has come a long way in the past few years. For better or worse, our buddy Elon. By the way, I miss old Elon. I miss the let's fly my sports car into space Elon. That guy was cool. This guy's crazy. But he also helped mature the lithium-ion battery to the point where they're now doing grid-scale power using lithium-ion. Now, lithium-ion is not well suited for this task. Lithium-ion batteries focus mostly on rapid charging, relatively rapid discharging, and lightweight, all things that are good for a car, but not especially important for grid power. We're making better lithium-ion batteries. We're starting to learn to optimize them for other roles. So the lithium phosphate batteries are a little better for this, but they're not optimal. There are better technologies out there. Now, there are big battery packs in Australia. They've got gigawatt packs down there. There's the Pillswood project here in the UK is about a 200 megawatt hour battery system based on the Tesla Megapacks, this exact thing that I'm showing you here. So there is a beginning of starting to create power sources that will bridge in between renewables and also for switching. Sometimes you want to switch from one source to the other, and lithium-ion battery packs can switch onto the grid very, very quickly. And so they're an alternative for temporary transfers and possibly even as far as a peaker plant. There are new battery technologies being developed. One of the folks that came from Tesla, but now is working on his own, Form Energy, has now got enough funding that they're building their first plants based on what's called an iron-air battery. So this is technology developed by NASA back in the 50s and 60s, and they've now pursued it further to mature it, looking at it as a better technology for the grid. Iron-air means much less expensive. Lithium is relatively costly to extract. Iron is extremely common. You are, yes, storing energy in rust, which is disturbing, but it's cost-effective. It also runs pretty hot. It's relatively large. But none of those things are important for grid scale. Right? In the end, the fact that it's big, hot, and heavy is fine. You're going to put it in an acreage behind a fence. The most important thing when you look at iron-air batteries is they have naturally long run times. So normal discharge rate for lithium-ion battery is typically 6 to 8 hours. It's about as long as you would normally get power from it. You can charge it up very, very quickly, but it won't really hold power forever. Iron-air batteries have about a 100-hour natural discharge cycle. And so they take longer to charge, but they hold that charge very well, and they can discharge over long periods of time. So they're better suited for overnight bridging of a wind farm. So you imagine building out a wind farm that while the wind's blowing, it charges batteries and provides electricity. When the wind's not blowing, you're getting that same amount of electricity from the battery system. The first of these are being deployed this year. Minnesota and Georgia are getting the first Form Energy plants. So they're at the beginning of this. Now, it wasn't that long ago that Tesla was deploying their first batteries, only 3 or 4 years ago. So we're making progress in this area. Far more common when it comes to storing power is pumped storage. So this is the idea that while I have extra electricity hanging around, I use it to pump water uphill into a reservoir. And then when I need it, I let it come back downhill and I spin turbines with it. There have been some dedicated storage sites. This is literally a diagram from a site in the US called the Raccoon Mountain Storage Site. So it was never a dam. It was literally built for the purpose of being pumped storage. And so it helps us offset when we have more power than we need. We can pump water uphill, but it's also becoming more common today to add to existing hydroelectric dams some pump storage capabilities, because we're finding more and more that our reservoirs aren't full all the time. The change in rain patterns and things have meant that our reservoirs are lower, and so we are being able to pump water back uphill when we have excess power. Back to that idea of putting solar panels on my reservoir, one of the things I can do with those solar panels is pump water back up into the reservoir. So the reservoir gives me my on-demand power, and then when I have excess power, I'm using solar panels to recover it. I know it sounds weird. It's like, hey, you just let that water go down to make the electricity? Like, why would you pump it back up? Typically, I have reservoirs sitting below the dam as well, or I have other sources of water that are coming through the area, and so I can pick up that water and pump it uphill when I have water available for that. So pump storage is the most common power storage system we actually have. They've been around a long time, but we're taking them more and more seriously. The current estimate between pump storage and some of the battery systems coming online right now is that the UK actually is capable of storing up to about 1% of the power that it consumes in a given day. That's still a lot of megawatts, but it also speaks to a lot further to go. So I've run down the different power solutions, and this is sort of where we are in society, where some power sources have gotten less expensive, some have gotten more expensive. Interesting that the the zero emission ones are becoming the cheapest, wind and solar. Natural gas is the next cheapest. It's still a petrochemical-based power source, but it's relatively inexpensive. Nuclear tends to be absurdly expensive. Coal has gotten more expensive over time. And gas peaker plants are costly, but they're different from the regular natural gas ones because they're fast on, fast off. And looking at the planet as a whole, we're a long way away from getting to full renewables. If you look at this graph, it's not going to make you happy. Down at the bottom there, that traditional biomass, that's burning wood. Would not recommend. But coal, oil, natural gas, the vast majority of all the terawatt hours made on this planet. And then up in this cluster right at the top is our various renewables, whether it's solar, wind, hydro. Nuclear is not technically renewable, but at least it's a zero emission power. Let's talk about hydrogen, not because the news is good. So there's three kinds of hydrogen, essentially, the way we've defined it. There's the gray hydrogen, which is really us taking natural gas and steam refactoring it so that we blow off the carbon dioxide from it and keep the hydrogen. So yeah, I'm using hydrogen. I just had to emit a whole lot of carbon dioxide to have it. It's also the cheapest way to do it. There's blue hydrogen, where we're still taking typically natural gas and blowing the carbon dioxide off it, but we're capturing the carbon dioxide. And then green hydrogen, the one everybody wants to talk about, which is where we use electricity to split water to create hydrogen and release oxygen as a waste product. So let's talk about the differences between them. So, vast majority of hydrogen production today, irrespective of using it in these new ways, but when we've always needed hydrogen, we've done steam refraction. So we pump in methane, our natural gas, and we burn it. We get it up to very, very high temperatures. There's a little bit of chemical reactions there, and we're able to peel off the hydrogen that way. And we make a lot of carbon dioxide. And there's a few different ways to try and capture that, and then you try and utilize that carbon dioxide. Sometimes it shows up in Coca-Cola. It takes about 6 megawatt hours of electricity to produce a ton of hydrogen. Hydrogen is very low density. And you'll make about 10 tons of carbon dioxide in the process for 6 megawatt hours of electricity. If you're willing to spend a bit more energy, there's this thing called methane pyrolysis. So now you're pumping the natural gas into the bottom of a catalytic reaction. You're pumping about 7 to 8 megawatt hours of power into it. That higher pressures and temperatures of chemical reaction actually blows the oxygen off the carbon so that you get dry carbon from it, stuff you can hold on to, and then you're emitting oxygen and hydrogen. So better. These are more expensive to build. They're not the cheapest way to do it. They are becoming more popular. We're seeing more plants being built this way because you can manage the carbon pretty easily. It's a dry, hard product. It's sellable too, but it's straight carbon. If you want to bury it, you do. And everybody's favorite, the green hydrogen, which is where we make hydrogen out of water. So what's the problem? Well, it was about 6 megawatt hours to make a ton of hydrogen in the gray approach. It's 40 for electrolysis. But yeah, you're gonna split it in half. You're gonna make 8 tons of oxygen for 1 ton of hydrogen. Hydrogen's very light, but oxygen's not a big deal. It's just not cost effective. It's incredibly expensive to make hydrogen this way. You need a lot of electricity to do it. And so it's why there's just so little of it in the world. They figure less than 4% of hydrogen production on the planet is done through electrolysis because it just is a massive power sink. They're getting better at building systems like this that can use excess power. Often we're making solar and wind when we don't need them. And it's a problem to manage that. And so one of the options is you switch over to an electrolysis method. And so you burn up that excess electricity by making hydrogen. So we've started to see combined cycle systems out on the floating arrays of wind turbines where they actually have the electrolysis unit on site and they're storing hydrogen on site as well as making electricity. And when there's excess electricity being produced, they can actually tell them to switch over and make hydrogen from it as well. It's clever. Long way to go. Let's go back to nuclear because I only talked about traditional nuclear and obviously the UK is doing some of that. But the hip new approach that's been talked about for years and years is small modular reactors. And this has been a pipe dream for a really long time, but 2022 was a good year. Because 2022 was the year that several different small modular projects got approved, and some even started construction. So the core concept, the most important thing you take away from understanding small modular is that the site that runs the power plant never handles the radioactive material. So the radioactive materials that go into these reactors are handled in a factory. So there's one place that's certified to process those reactors, to actually assemble them, to handle the nuclear material. They put together a small modular reactor, the kind that can fit on the back of a truck. I know it seems weird to want to move that stuff around by truck, but if you're building nuclear power plants, you move reactor fuel around all the time. This, we're made them small enough that the whole reactor fits in. And so a given site would have a bunch of reactors. They typically run for 2 years before they need refueling. So you stagger their implementation. You can take them out and reprocess them. They tend to be small enough that they can't actually melt down. They don't have enough fuel in them. So you never wreck the site. You can wreck the reactor, but then you take the reactor out and haul it away. So there's a few things that come from doing it this way. You have one place to get certified for handling nuclear fuel, the factory. Sites don't need as much containment. They don't need the biggest perimeters. They don't have any fuel handling. They just take old reactors and replace them. You also means that every couple of years, you get to upgrade reactors. So rather than us building out these bespoke, massive concrete things distinct to one implementation of power, and then after 30, 40, or 60 years, we get to do something with it, or we shut it down in mid-usage to do modifications to it. Every 2 years, you get to put a new reactor in. Now, most small modular are this is the design from NuScale. This is now an approved design by the Americans. The National Nuclear Service approved this reactor. It can now be deployed. That being said, nobody's buying at this particular point. There are several interested parties. But these are only 60 megawatt reactors. They're relatively compact, which is why they fit so neatly the way they do. In Canada, Ontario specifically, 80% of its power comes from nuclear. Mostly the CANDU reactor, which is a particular design, but those designs are aging out. They just approved a location to put a small modular reactor design from GE Hitachi. It's not that small, actually. It's a 300 megawatt reactor, so it's a pretty good size. But it is developed and constructed off-site and then put into place. And same thing, it's going to have runtime for a couple of years, and then they replace it with a new one. And so the idea being that over time, we build a factory or two, and we keep improving reactor designs and rotating through different sites. And where you're seeing 10 to 20-year construction times for reactor sites because of all the bespoke behavior and certification and so forth, they're talking about being able to build them in 48 months. But they haven't done it yet. So I expect the Darlington site, which is in Ontario, which is underway, to go over time, because it's the first. But at least the methodology they're using gives us a hope that we could do this quickly. What we like about these power technology is no emissions, simple, reliable operations. We've now matured most of the big problems out of it. It doesn't need a lot of external support. It doesn't need a constant supply of fuel coming in. You're talking about refueling every couple of years. So, and in Canada, where we have very northern areas where there's, where solar and wind are simply not feasible, these small reactor designs might be exactly what we need to support those folks up north. Because right now, they're burning diesel. And that's not good for any of us. The folks at Rolls-Royce have a design. They're very keen to get certified for about a 450 megawatt modular reactor that they want the UK to support specific to here. So you may have seen it on the news. They were talking about it fairly recently. It looks very similar. It speaks to these same key issues. Central location for manufacture, can be deployed to multiple sites, one location to certify, and then the actual reactor sites don't handle materials. So let's be funner. We're geeks. Let's talk about fusion. I don't know if you've noticed, but they've been building a plant in France for a really long time. There's the Joint European Torus jet, which is actually here in the UK, built in the 1990s, and it does deuterium tritium fusion. It does it with copper coils to compress a plasma to the point of fusing, which really did work. And its best run ever was in 1998, when they put 16 megawatts of energy into the plasma and got about 14 back. They didn't capture it, that's what they measured. So it was a Q of 0.7 or 0.69 at the time. It was a big deal at the time. The reactor design is relatively old. It's from the 90s. ITER, the big upgrade for ITER, it's a much larger reactor, but they're also using superconductive magnetic coils. They use niobium tin cooled in liquid helium to compress the field, or at least they will someday. They've been building it for a really long time. Because it's an international consortium, that torus, the donut that's being built there, is being built in 8 segments in 8 countries. Because that's an efficient way to do things. But remember, this is one of the ways you get, this is the same reason they did this with the International Space Station. When you get multiple countries involved in these treaties and so forth, you're more likely to actually finish it. The Americans started out going on their own. They were going to build their own giant torus, and they could cancel that. The next administration came in, and it went away. So now they're participating in ITER. ITER's supposed to get to a Q of 1. So same amount of power in, same amount of power out. It's still a test design. There are more advanced designs out there. So the folks at MIT have a company called Commonwealth Fusion, where they're using REBCO field coils. So niobium tin is sort of a traditional superconductor cooled with liquid helium. REBCO, it means rare earth barium cupric oxides. You've seen all these little videos of them with a petri dish with a little cube floating. They pour liquid nitrogen over to make it float. That's a REBCO. They're ceramics, so they don't make good wire. It's taken decades for them to figure out how to actually turn it into a film that you can wrap into a coil. And the Commonwealth Fusion folks have built the first part of their reactor and showed they can really make a superconductive coil, cooled liquid nitrogen, much less expensive and difficult, but it makes a much more powerful magnetic field than niobium tin. It's a breakthrough. And so their reactor is smaller, cheaper, and lighter, and good enough that Bill Gates kicked in a whole bunch of money. So we may actually see a reactor one of these days. The problem, of course, is that deuterium-tritium fusion, I'm going to say, of course, like all of you are up on this. So what is deuterium-tritium? These are isotopes of hydrogen. Regular hydrogen has a proton and an electron. That's it. If you get a neutron involved, that's deuterium. Deuterium is naturally occurring. It's about 1% of seawater. The water is actually heavy water, being that it has deuterium as the hydrogen atoms in the water. Don't drink it. Apparently it's sweet. It's just not good for you. Okay? And we can extract that, and in the CANDU fission reactors in Canada, we use heavy water because those neutrons are useful for power exchange. Tritium, you have 2 neutrons. Now, when you're doing fusion, you're making helium out of hydrogen. So you're banging the hydrogen together so hard, the protons end up sticking together. And they really like doing that, so they complain loudly to management in the form of a very big burst of energy. But helium needs a pair of neutrons to be stable. And so by using tritium and deuterium, you have 3 neutrons available, and so they slam together, and 2 of those neutrons become the helium, and one of those neutrons spins off. And that becomes our best opportunity to extract power. Except that neutrons can't be contained by magnetic fields because they're neutrons. And so they actually do a lot of damage. The jet torus, when they did those big runs with it back in the day, it basically powdered the inside of the containment vessel, the neutron damage from it. So if we were actually going to make a power plant like this, we have to understand that A, you need a ton of tritium. Tritium is not naturally occurring, you have to make it. So you have to actually run a machine that breaks lithium apart to spit out tritium. That's going to consume a bunch of energy. That makes you enough tritium to run your DT fusion, but you're going to routinely, now you have to capture neutrons in a useful way. I would recommend a big wall of molten lead, which takes a lot of energy to run, but you're going to capture that neutron in there and generate more heat, and that should give you enough to spin some steam turbines. But it isn't going to be free. It's not, you keep talking about making power from seawater, so, except for the tritium. We could do other kinds of fusion. There are kinds of fusion called anisotropic fusions. That's fusions that do not emit neutrons. And if you're interested in this stuff, I would go look at a company called Tri-Alpha Energy. They have a pulse reactor design that could get to the point, it doesn't yet, of doing proton-boron fusion, but it needs about 100 million degrees as opposed to about the 10 million degrees needed for DT fusion. The other improvement, besides these new kinds of coils, is we've started using machine learning models to understand plasmas. And so we're now going to use sophisticated software based on machine learning to manipulate plasmas to keep them stable for longer so we can generate more energy. So there's been some good technology developed over time of studying fusion. If you think fusion's just not made any progress, I'm here to show you the little bits that it has. They used to say, fusion's only 30 years away, and it has been 30 years away for 50 years. Now it's about 20 years away. And the problem is it's billions to go. And so considering the crisis we have and the interest we have in making cleaner power right now, as much as I love this, it's not the best use of money at the time. I'd rather be building a lot more small modular reactors to make zero-emission energy and spend less on this if I have to trade the two. I prefer not to trade the two. I'd like us to do both. The fusion power has a whole lot of benefits for things like buying a bill of flying spacecraft and thing long term, but it's a long way from being a power source still. We are getting smarter about our grids. So we're learning to make power in more places. That's been part of the problem with getting good at wind power and solar arrays and so forth, is we're used to having a few large power plants and making it pretty easy to keep the grid stable. Now we're having lots of different power plants, including power right at the house. So this is where we get into the whole conversation about residential solar, that our houses can be part of operating themselves. The power companies don't want you to sell power back to them. It's not easy to use. In fact, it's largely impossible to use, but it's one of our incentives to do that. What they really like about you generating your own power is that you stop consuming theirs, at least at times. And so that all that offset mechanism is secondary. What you're seeing now is that we're getting local battery solutions as well. These are the Tesla power walls, and so they work very neatly with solar to offset the power. The reality for us is that our power consumption varies over the course of a day. Typically, the highest power consumption in a given day is around the time everybody gets home from work and kids are back and it's time to make dinner. And you're probably going to run the hob, you might run the dishwasher, you may even be doing dishes. It's a huge spike in power consumption for an hour or so. And if you got an electric car, you plugged it in when you came back. So you kind of made the worst case scenario. And they pretty much have to provision for all of that power at once. And that's when they turn on peaker plants and other nasty polluting things. What if you could be using your batteries at that moment? The power you collected over the course of the day with whatever little sunlight we got that day, there was a little today, gives us enough power in that we got maybe 14 kilowatt hours of electricity in these two power walls, and that should be enough to get you through dinner. Better still will be to make our appliances smarter so that we don't do dishes immediately. We make sure they're clean by morning. We're getting pushed to use more and more electricity, actually, right? They're saying stop using gas for your heat, use a heat pump, more electricity. They're asking us to use induction stoves, which, by the way, are very cool, but also consume a lot of electricity. So we're going to increase our dependence on electricity to decrease our emissions, right down to the electric car as well. The electric car is an interesting option. Because it's a pretty good battery, we are starting to see systems now where we can use that battery for our homes. It's not necessarily good for the battery. That battery is designed to work the way a car works, where bursts of power and then charge later, where the way we consume power in a house is a little different from that. But in general, for us as software people, the opportunity to make the house smarter all around so that we can communicate with the power grid and have variable rate electricity. We're seeing some places now where the price of electricity varies hour to hour. So you can imagine with some good software with your appliances, you could be telling your dishwasher, hey, make sure these dishes are clean by morning. You loaded it at night, but you won't wash it till sometime in the middle of the night. Now you could figure that out. Hey, maybe 4 a.m. is the right time. But better with a smart grid that it'll actually say, okay, well, I can run this off a battery. Or maybe the local wind turbine kicks up because it's windy right now, and that's basically free power, so I'll do it now. Right, that ability to select and also to converse with the grid and to offset so that the grid has an easier time of dealing with these things. I work with some folks in the Netherlands that are doing this with their electric cars because the electric car demand around dinner time was so bad it was browning out the affluent neighborhoods because they're the ones with the Teslas, right? And all you got to do is brown out one affluent neighborhood, and boy, action gets taken. And so now there's the power points in that part of the world. When you plug it in, it negotiates with the grid for when to charge. And it'll do an assessment like how much charge have you got, and can it get you to the hospital? If it can't, okay, I'm going to give you enough power to get to the nearest hospital, and then I'm going to wait. And later in night, I'm going to offset charging for all the cars in the homes in that area so that we don't stress the grid and everybody gets a charge by morning. We've got work to do as software people with all of these things. It's interesting times. They're going to make better and better power sources, but they're also asking us to use more and more electricity. So we're going to have to get smarter about it. And nobody wants to pay attention to this stuff. 12 cents a kilowatt hour or even 20 cents a kilowatt hour is not enough for you to pay attention, but our software could. I hope this was useful for you. If you haven't run across the show before, there's a shortcut link called geekout.show that'll take you to the 100 or so geekouts we've done. I'll continue to do them at least once a year on these topics and the space ones, and maybe a couple others if you ask. Thanks so much for your time.